Hi and welcome to this Junior Cycle Higher Level Maths video where we're going to look at geometry and specifically the circle theorems. In this video we're going to review the theorems very quickly and work through some exam style questions. Linked below is a video that goes through the circle theorems in a lot more detail. It's an investigation, and if you feel that you need a little bit of work before you look at the exam style questions, go to that video first. Let's do a very quick review of the parts of the circle, which will help as we're using terminology throughout this video. So the first part here is the outside of the circle, that's known as the circumference. The second is a line which goes from the center of the circle out to the circle, and that is known as the radius. The third one here is the line that goes from one side to the other and through the center, and that is known as a diameter. The length of the diameter is always double that of the radius. So if you know the radius, you can get the diameter very quickly, and vice versa. The next one we have here is a line that goes through the circle but not through the center, and this is known as a chord. Now, a chord can be any line which goes from one side of the circle to the other, so technically the diameter is a special chord which goes through the center. The next one we have here is a line outside the circle, and this is known as a tangent. A tangent is a line that touches the circle once and only once. Then we have an arc, which is part of the circumference of a circle. And then just the final two, be very careful, these are often mixed up. 7 is called a sector. It is the slice of pizza, which means it has two radii on either arm and then an arc around the edge. And then 8 is a segment, which is a part of the circle cut off by a chord. So the first theorem we're going to look at today is theorem 19, which basically says that the angle standing at the center of the circle is double the angle which stands on the circle once they stand on the same arc. And what we mean by standing on the same arc is that they both start and end at the same point. And here is our arc there. So corollary 1 of theorem 19, a corollary is just an add-on to the theorem. It states that all angles at points of a circle standing on the same arc are equal. So again, here we have them standing on the same arc. They're starting and ending at the same point, and those two angles are equal. This is known as the bow tie rule because of how it looks like a bow tie. So next we have corollary 2 and corollary 3. Corollary 2 says that each angle in a semicircle is right angled. Corollary 3 is that if an angle standing on a chord BC at some point on the circle is a right angle, then BC is a diameter. They're not an exact converse, but just for simplicity, what I'd say to you is think of them as they are the opposites of each other. They are like converse theorems. And finally, corollary 4 tells us that if ABCD is a cyclic quadrilateral, and just to remind you, a cyclic quadrilateral is a four-sided shape where all the vertices are drawn on a circle, then the opposite angles sum to 180. So in this diagram, A plus C add to 180 and B plus D add to 180. The converse is also true, that if you have a quadrilateral where the angles, opposite angles add to 180, then it is a cyclic quadrilateral. So just some things to remember is that actually a cyclic quadrilateral is a quadrilateral where a circle can be drawn. So even if the circle is not there, it can still be a cyclic quadrilateral. Example 1. So this is an exam style question, so it didn't come from our exams, but it gives you an idea of how we can work with it. So a diagram shows 4 points, A, B, C, D on the circumference of a circle. BD is a diameter and ABCD is a kite. Now officially kites are not something that we study, but we do see them pop up, but they're well explained what they mean. So a kite is where two sides are equal, but unlike a parallelogram, they're actually sides beside each other, not across from each other. So you can see on the diagram here how they've shown us that AB, the length of AB is equal to the length of BC, and the length of AD is equal to the length of DC. And the question is find the value of x. So what we have here is actually two congruent triangles. So two triangles that are identical. That means that they have three sides in common. So side, side, side. So if I just take my highlighter, so this side matches this side because we were told that. This side matches this side because we were told that. And then this side BD is actually common to two triangles. So we have two congruent triangles, which means that this is also 20 degrees and this is also X. So we can work with either triangle. Think about your circle theorems, and the theorem that we're going to use is the angle drawn in a semicircle is always right angle. So these two angles here, the one at A and one at C, are both 90 degrees. So then for X, it's going to be 90 degrees plus 20, which is 110 degrees, and then it's 180 degrees, take away 110, and that leaves us 70 degrees. So X is equal to 70 degrees. You can work that whatever way you want, but the idea here is using that circle theorem, well, one of the corollaries, that the angle in a semicircle is a right angle. Example 2. So this is from the 2016 paper 2, and it's question 7. So it tells us that the points A, B, C, D are shown on the diagram. They are all on the circle K. It tells us the length of AB is equal to the length of AD, which is given to us on the diagram, and the length of BC is equal to the length of DC, which again is given on the diagram. So effectively what we have here is another kite. The size of some of the angles are marked. Calculate the value of X. So the first thing I would say is that we have a cyclic quadrilateral. So a cyclic quadrilateral, which means opposite angles add to 180 degrees. So 100 degrees plus X should add to 180 degrees, which gives us X equal to 80 degrees. So nice and straightforward for the first part of that question. So part B asks us to calculate the value of Y and show all of your workings out. So at the moment, all I have here is a cyclic quadrilateral, and I need to do something more. I need to find out more information. And often what we have to do in geometry is add a construction line. So putting in a line that is beneficial. Now, I'm going to go with triangles. So we have two options. So one option is we can draw the line like this. I like that idea because we end up with isosceles triangles and we can work with them. So here, if we remember, X was actually 80 degrees here. And what that allows us to do, if we've 80 degrees here, then we've 100 degrees left in the circle, which means I have 50 degrees here and I have 50 degrees here. Over in the second triangle on the left hand side, I have 100 degrees in that angle. So that means there's 80 to be split between the bottom two. So that's 40 and 40. So Y would be equal to 40 degrees plus 50 degrees, which is 90 degrees. Now, a second line that you could put in, so we could connect here A to C, and it feels like we've less information. So a bad thing would be to do an assumption here, and we do not want to assume anything we don't know is true. However, what we do know is that this line has created two congruent triangles. So congruent, remember, means identical, and we can say that under SSS, so side, side, side. So the sides here that are common. What that means is we've two identical triangles, which means that this angle must be 50 and this is 50 because they're going to be identical angles. If we remember, X was 80, so this must be 40 and 40, and then we could work out Y as 40 plus 50 is 90. So 40 and 50 is 90 degrees, and then 180 degrees minus 90 degrees is our 90 degrees, and that gives us our Y. So that's an absolutely valid approach as well. What's really, really important is we just don't assume that AC is the diameter. We don't know that. Now, when we find out that Y is 90, then we can use that idea of corollary 3, which was like the converse of corollary 2, that basically said, if I have a right angle triangle in a circle, then the base must be the diameter. So AC must be the diameter. So now we know that, but we cannot make that assumption. So example 3 is from the Edco Sample paper, so it's Sample A Q7. What I actually really like about this is it's basically a version of a question that appeared on the Leaving Cert high level paper. Now that might freak people out, but I don't say it to freak people out. I say it as in, you know, most of the geometry that you're doing at junior cert higher level is all that you really will need moving forward. The questions can get a bit trickier, but actually there's nothing really new that you have to learn. There's a few little theorems thrown in, but the bulk of what you have at Leaving Cert is what you've learned for junior cert. So learn it well. So a really good technique when you're doing any kind of questions with diagrams is to read through the paragraph that you're generally given and to make sure that every piece of information you're given is on the diagram, and if not, put it on the diagram. So in the diagram below, O is the center of the circle S, which means BC is the diameter of S. Now looking at the diagram, yeah, O is the center, so BC would have to be a diameter. It tells me that BCD is 90 degrees, and that's given on the diagram. It tells me that the chord GH is parallel to BC. Now, that wasn't given, so I'm going to throw in some little arrows to kind of help me there. And it tells me GH is equal to half of BC. Now, that's really interesting because remember, BC was the diameter. So if I asked you what is half the diameter, hopefully you'd be able to say it's actually the radius. Now, I'm not saying GH is the radius. What I'm saying is the length of GH is equal to the length of the radius. And why that's interesting is because we're going to start playing around with these triangles. So bear in mind here that the length of GH is going to be equal to the radius. So going to my diagram, what I know is O to G is a radius, so that length there will be equal to OH, which is also a radius. So I end up here with a little isosceles triangle. OB is also a radius, so actually I have two little isosceles triangles, and that's something that's often missed. Now remember that GH was also the length of the radius, so if I put in those markings, effectively what I have is an equilateral triangle there. So I end up with an equilateral triangle, and the first question is to show that GOH is equilateral. So I just need to explain my reasoning. So I suppose OG is equal to OH, and the reason is that they're radii, plural for radius. GH is equal to radius above, and I can just draw a little arrow. Therefore, triangle GOH is equilateral. So that's all we really needed to do. Now, what's interesting when we're working with an equilateral is all the sides are equal. So it's my not so great equilateral. All the sides are equal, but all the angles are too. So 180 degrees divided by 3 gives me equal angles of 60 degrees. So I have 60 in all of these places here. So if I go back to my diagram, I have 60 there, I have 60 here, and I have 60 here. And now we can proceed with the next step. So part B asks us to work out the angle BDC. So it's asking us to work out this angle here and show your calculations. So I suppose my first thing I'm going to say is, well, look, I have this triangle here. And it's easy with all the noise of what's going on within that triangle not to see it. But I have a big right angle triangle. And I already know that it's right angle, so I know one of the angles. So if I was able to figure out just this angle here, then actually I will be able to work out the angle that I need. Now think about all the information we've used. So we'll have used that 90 degree, we'll have used this piece here. This little question or this little statement here is interesting. The chord GH is parallel to BC. So anytime you see the word parallel, two words should come to mind: alternate and corresponding. So we're working with either alternate or corresponding angles. So I'm going to take just a colored highlighter, and I'm going to say, well, here's my parallel line, here's another parallel line, and here's my transversal. And I know a little 60 degrees in there, so in here, so actually this angle here is also 60 degrees. So using that idea of it being alternate. Now, I've colored it in, so I'm going to have to just get rid of this for a second. If you remember, I'm just going to get rid of those lines for a second. We've already said that OG is a radius and OB is a radius. Therefore, that triangle OBG is an isosceles triangle. So if I have 60 degrees there, I'm going to do 100 degrees minus 60 degrees, which is 120, and then I can divide that between the two bottom angles, which gives me 60 degrees. So that's 60 degrees here and 60 degrees here, which actually means that OBG is not isosceles. It's actually one step further. It's actually equilateral. So effectively now what I have is this big right angle triangle where we want this angle. We know that's 90 and this is 60. So what I can do is 180 minus 90 minus 60, and that equals 30 degrees. So I get angle BDC is equal to 30 degrees. So a lot going on there, and I suppose one of the big takeaways from that question is using the radii as equal sides and remembering that they are equal. And I know you know that. It's just to be very, very blatant about that when we see a question. So example 4 is an Edco Sample D Q13, and in the diagram BC is the diameter of a circle with center A. ABD is 53, the length of DC is equal to 8, and the length of AD is equal to X. Find the value of X. Now it's interesting because they want a length this time, and I suppose anytime we're working in triangles and need to get the length of a side of a triangle, we're really limited to doing either similar triangles, which it doesn't look like we're going to have here because we don't have enough side information, or trigonometry. In order to use trigonometry, we need to have right angle triangles, which we don't have. So just, I suppose that should be our way of thinking. Now, I'm going to fill in as much as I can. So the first thing I'm going to do is I'm going to say, well, AB is a radius, AD is a radius, AC is a radius. So they're all equal, which creates these equilateral triangles. So this is 53 degrees here. So then I can work out 53 plus 53 is 106 degrees. So this angle here is 74 degrees. Out of 180, this one here is 106 degrees, and then I can work out my little angles at the side. You could also use the fact that the angle here at D is going to be a right angle, and that's absolutely fine. This works out as 37 and 37, whichever way you want to work. So a few different ways there that we can work. Now I need to focus on getting X. I'm going to work with the triangle ADC because that's the one where I actually have the most information. So I'm just going to get rid of this 106 because it's not terribly helpful at the moment. And what I'm going to do, if you think back to triangles, and the triangle video is linked below, I'm going to drop a line from A to the base that perpendicularly bisects the base, which means it cuts it in half. So it means this length here is now 4. So I'm going to pull out this triangle just to give myself a little bit more space. So this is the triangle I have. I have right angle, I have 4, I have 37 degrees, and I have X. Now I can use my trigonometry ratios. So that is sine, cos, and tan. So first step is to label. This is my adjacent side. This is opposite, but I have nothing, so I'm not going to use it, and hypotenuse. So go through SOHCAHTOA, or however you remember sine, cos, and tan. We are actually working with cos. A is equal to adjacent over hypotenuse, which is the cos of 37 degrees is equal to 4 over x. And now we need to work it through. So the first thing we can do is actually work out what cos 37 is. So let's do that first. Cos 37 degrees, and it is 0.7986. I'm going to go to 4 decimal places, is 4 over x. I'm going to multiply both sides by the denominator, which in this case is x, and don't panic too much about that. I know it is an unknown, it is a variable, but that's still the rule. So don't try to multiply by something else because you don't like the x. The rule is you multiply by the denominator. So what we end up with is 0.7986x is equal to 4. So to get x, we divide by the coefficient. Again, even though it's a bit nasty, even though it is a long decimal, we're dividing by that. So we get 4 divided by 0.7986. And I get x equals pretty close to 5. So a tricky little question here, and I suppose really showing us how all of the geometry is interlinked, and also how closely geometry and trigonometry are interlinked. So don't think, because I have a very obvious circle with lines in it, that it's circle theorem and only circle theorem. Think of everything else that can be brought in. Example 5 is from the 2014 paper 2, and it's question 10. It tells me that A, B, C, D are 4 points on the circle as shown. It tells me AD bisects angle BAC. So what that means, and what's not on the diagram that we're going to put in, is this angle equals this angle, because AD has bisected angle BAC. P is the point of intersection between of lines AD and BC. You can see that. Show that angle, so show that triangle ADB and triangle APC are similar. So what we mean by similar are they have equal angles. So we're trying to prove that all 3 angles are the same. Really, we only need 2 angles, because once 2 angles are the same, the third one has to be the same. Just for ease, I need to see which ones we're working with, so I like to use a bit of a highlighter. So A, D, B, so that's my yellow one there. I'm just going to put a little tag next to it. And then APC, which is this one here, which is green. Okay. So we need to prove that they are the same. So let's start with the obvious one that we were given. We were told that angle BAD is equal to angle PAC, and the reason is AD bisects. So we're told this AD bisects, which means cuts exactly in half, angle BAC. Okay, so that's one angle. Now, the second one, I suppose we are dealing with circle theorems here, so really think about your circle theorems. So what I would see is this angle has to equal this angle here, because they're standing on the same arc. So they both start at A and end at B, or the other way around if you prefer. So you can see AC to B, AD to B. So we have on this triangle angle ADB, and that equals angle ACP. Apologies. And the reason is angles standing on the same arc. So that was our bow tie rule on the same arc. Now once you've proved 2, that's all you need. So what we can then say is, well, ABD in this triangle is equal to angle APC, because it's the third angle in a triangle. That only works for angles, because we know that all the angles in a triangle add up to 180. So if 2 angles are the same, then the third one has to be the same. So third angle in a triangle. And then we can say, therefore, triangle ADB and triangle APC are similar. So a little bit of practicing on our informal proof, so showing that 2 triangles are similar. So just be really, really clear the difference between similar and congruent, because these questions are, they have the same kind of layout, but very different approach with what you have to do. So here there will be more questions, but we'll just look here at that similar piece. Example 6 is from the Edco Sample Paper E and it's question 11, and this is an algebra based question. So what we have is two unknowns, x and y, and we're trying to solve for both of them in the diagram. What we have here is a cyclic quadrilateral, so we have a four-sided shape, it's irregular, but all of its vertices sit on a circle. What we know about that is opposite angles add to 180. So I know that 100 plus 5 times x will have to equal 180 degrees. So by solving that, I find, well 5x then would have to be 80 degrees. So x will be 80 divided by 5, which would be 16 degrees. Then looking at the other set of angles, I would find y plus 8x minus 13 should also equal to 180 degrees. I know that instead of x, I can put in 16. So take away 13 is equal to 180 degrees. So 8 times 16, that gives 128, minus 13, which is 115. So y plus 115 is equal to 180. 180 minus 115 gives us 65 degrees. So that is our x and our y. So quite a straightforward little question, but given that circle theorems in themselves can be quite tough and there's a lot to remember, putting in algebra can be quite intimidating. So I suppose it's just to see that this is probably one of the more straightforward questions that we saw in this video.